Welcome to video 13 in the TTb course. This video marks the start of part 4 of the TTb course. In part 4 we consider techniques for monitoring TT systems. In this video we consider power-on self-tests or posts for TT systems. The material in this video is based on chapter 13 in ES 2. As usual, I suggest that if you haven't yet read this chapter, you stop the video now, read the chapter, and come back and start the video again. When you're working with reliable embedded systems, one of the questions that you need to consider constantly throughout the development process is, what can possibly go wrong? You should have this on every whiteboard, the top of every whiteboard in the room that the development team works in. This is the key question you should be thinking about during the development process. Even if we've got a perfect set of requirements, even if we've produced a great system design, even if we've tested it thoroughly before it leaves the factory, there are still many possible things that can go wrong at runtime, and we need to be sure that if these things happen, we can detect that they've occurred and that we can handle them in an appropriate manner. For example, electromagnetic interference, lightning strikes, radiation, high temperatures, low temperatures, flooding, vibration, high voltages, low voltages, chemicals. We might have the wrong software running. There are probably still bugs in the software. We may be subject to deliberate software changes, such as computer viruses. There may well be hardware bugs. There may be some deliberate hardware changes. There may be sensor faults, actuator faults. There are many things that can possibly go wrong between your system leaving the factory and your system being used in the field, potentially for many years. For example, an aircraft flying for a long time, 20 plus hours these days, faults may occur in the engine. Will you be able to detect these? Will you be able to handle them appropriately before, for example, you suffer from a severe engine fire? If you're developing missile systems, clearly you want to be sure that these will not be triggered at the wrong time. If you're developing safety systems, advanced driver assistance systems, basic safety systems for use in an automotive environment, you need to be sure again that mechanisms won't be triggered at the wrong time. You might like to do a search on Google for the Honda watermelon airbag, which is an interesting example of what happens when an airbag isn't triggered correctly. You might be building security systems that are used in otherwise safety-related systems. We'll talk a little more about this when we look at some of the case studies later in this course, but you can easily imagine that if you're going to create a mechanism for locking a vehicle, and in particular for locking the steering column in a vehicle to prevent theft, we need to be comfortable that this locking is not going to take place while the vehicle is in use. If you're going down a motorway and the locking bolt is inserted into the steering column, this could clearly have fatal consequences. Simple washing machine, simple microwave oven, similar problems in each case. When the door is open, the drum should not be rotating in the washing machine. When the door is open, the microwave source should not be active in our microwave oven. So how do we monitor TT systems at runtime? A key reason for choosing a TT architecture is that the resulting platform will have deterministic behavior. We can therefore, as we've seen, model key characteristics such as the maximum CPU load, the response time, and levels of task jitter. And we explored these matters in part 3 of this course. Now, such models are necessarily based on various assumptions, including the following. We have operational peripherals on each processor. We can transfer data between tasks on the same processor without corruption. We can transfer data between processors without corruption. We explored techniques for testing these assumptions in part 2 of this course. The models that we presented in part 2 of this course also assumed that all the processors in our platform are operating correctly, that we are running the correct processor software on each processor in our platform, that we have an operational scheduler on each processor in our platform, that we know the worst case execution times and probably the best case execution times of all tasks on each processor in our platform, and we know the execution sequence of tasks in each mode on each processor in our platform. If we fail to meet any of these assumptions at runtime, our models may not be valid, and we cannot be sure how the platform will behave in the field. We therefore need to incorporate mechanisms in our design that will allow us to test these assumptions at runtime, and we need to consider what we will do if the system does not pass one or more of these tests. The development of effective runtime monitoring components is a key part of the design process, and, in many cases, around 50% of the platform software is likely to be devoted to such monitoring activities. In this video, we will begin to explore POST, Power on Self-Test requirements. The acronym POST is used in this course to describe a suite of tests that need to be performed before a platform can start or operate in a normal platform state. The acronym is usually expanded as Power on Self-Tests, which is what we'll use here, or sometimes as pre-operation self-tests. There are two forms of runtime tests that are usually performed: POSTs, Power on Self-Tests, and BISTs, Built-in Self-Tests. The POSTs are carried out when the system is powered on. The BISTs are carried out usually periodically while the system is executing. Not all systems need BISTs. If the system's run for a very short period of time, then we may not require BISTs, but we usually do. Almost all systems require POSTs. It would be very surprising to create a safety-related system or any form of reliable embedded system that did not require at least some form of power on self-test. We're going to look at POSTs in this video and in video 14, and we're going to look at BISTs in video 15. But from this point onwards in the course, the use of POSTs and BISTs will be a key part of what we discuss in many of the videos. So let's start by looking at what's required when we do power on self-tests. This is a list of our recommended processor checks. We'll use an independent clock source to check the oscillator frequency. We'll use a suitable library to test RAM memory and CPU registers. We'll use a golden signature to check the executable code. We'll test the memory areas used to store register variables. We'll test the internal watchdog timer. We'll use the watchdog timer to check the scheduler operation. We'll perform startup checks on all peripherals used in the application. We'll check the external watchdog controller if this is present. We'll check the monitor unit. We'll check the predictor unit. We'll perform key environmental checks, such as measuring the ambient temperature and the processor operating voltages. We'll use a warranter to check for security infringements if this is deemed to be necessary. And we may use a second processor to perform additional checks on the platform, including the schedulers, the interrupt system, the operating frequencies. As you can see, many checks are required at startup. And, as we've already noted, we also need to carry out BISTs while the platform is running. You can begin to see why 50% of the processor software may be made up of monitoring components. So let's begin by looking at some of the low-level POST operations. We will typically aim to investigate some or all of the following elements during power on self-tests on each processor in our platform: the clock frequency, the program counter and other CPU registers, the RAM, the ROM or flash memory, and the interrupt operation. The key question that we're trying to answer through the use of such low-level POSTs is as follows. do we have an operational processor to work with? If the answer is no, then all we can do is try to enter a fail-safe processor state. And you'll recall that we've been using a fail-safe processor state and beginning to implement such a state since video 2 on this course. The challenge here is obvious. If our processor is based on a single processor and this fails its power-on self-tests, it's very difficult to be confident that this processor will be able to perform the operations that are needed in order to fail safely. If we have only one processor in the platform and failure of the posts could result in a dangerous situation, then we need to consider incorporating an external watchdog controller, something we'll talk about in video 17, a warrantor unit, something we'll talk about in video 20, and/or we need to consider migrating to a duplicator platform or another multiprocessor platform. We'll discuss such platforms in video 21. The key thing here is, unless you can be confident that you will be able to enter an appropriate safe state in the event that you fail your posts, you need to consider whether simply basing your system on a single processor is an appropriate thing to do. So let's begin by considering how we can test the clock frequency. The typical way that we test the clock frequency in a single processor design is that we base the design on some form of external crystal oscillator, and we use an internal RC oscillator or similar on the microcontroller as a simple benchmark to check that the external oscillator is operating at roughly the right frequency. Since the external oscillator is likely to be stable, have a stable operating frequency even over a wide range of temperatures, and the RC oscillator is not likely to share these characteristics, use of the RC oscillator to check the external frequency is a reasonable solution, but it's not perfect. We're not going to be able to determine that the external oscillator is operating at plus or minus 1% of its required frequency, for example. So this is a way of simply determining that the external oscillator is operating at approximately the correct frequency. If you need a more accurate check than that, you need to consider alternative options. Sometimes an external clock source, sometimes even the mains power supply, can be used as a way of providing a slightly more accurate frequency benchmark that we can use for testing purposes. Alternatively, we may have multiple processors in our design, in which case we would do some initial checks, local checks, to check that the oscillator was operating by comparison with the RC oscillator, and then after we had both processors up and running, we can perform more accurate cross-checks, much more accurate cross-checks between the two microcontrollers. This is an approach that's often followed in duplicator platforms, for example. Next thing we'll consider is the testing of memory. In terms of testing flash memory, we'll discuss this in the next video. In terms of testing RAM and registers, the tests will typically start by determining whether the memory cell under test is stuck at a particular value. Tests will also be made for coupling between memory cells. For example, if we change the value of only one bit in memory, this should not have any impact on any other memory cells in the device. Transition faults may also be tested. For example, under some fault conditions, the value stored in a cell may be able to change from 1 to 0, but not from 0 to 1. We need to test for this. To test volatile memory during power-on self-tests, some form of marching algorithm is commonly employed. Such tests involve combinations of write operations followed by read operations that are carried out by moving or marching up and down the memory area that is under test. Next, we need to test the interrupt operation. Checking that interrupts are operating correctly may be challenging in an event-triggered design. There may be a number of interrupts, and we don't know when those interrupts should be triggered. In a TT design, interrupt tests are comparatively straightforward, not least because we typically have very few interrupts. Where we have no external monitoring available, an IWDT linked to an RC oscillator will often be used to check the rate at which scheduler interrupts occur. We'll say more about this in video 16. When performing many of the tests we've just discussed, we need to use suitably qualified test libraries. For example, for systems developed in compliance with IEC 60335 or IEC 60730, libraries supporting designs up to Class B are available, usually without charge, from various MCU manufacturers. For designs in compliance with standards such as IEC 61508 and ISO 26262, development teams need to create their own libraries or use appropriate third-party libraries for this purpose. Any code library employed in an IEC 61508 design, for example, needs to either have been pre-qualified by the supplier of the code, or it needs to be revised as necessary, for example following Route 3S, as we discussed in video 10, in order to ensure that it is of a standard that is suitable for use in such a project. Other international standards such as ISO 26262 place very similar requirements on the development team. And as we discussed in video 10, it can be challenging to ensure that an off-the-shelf library, for example a library provided by the MCU manufacturer, is of a suitable standard to meet the requirements in a safety-critical system. As an example, there's a code library available that supports power-on self-tests in compliance with IEC 60335. This table is taken from NXP application note AN10918, and this shows the support provided by this particular library for this particular range of microcontrollers. Similar libraries are provided by other MCU manufacturers. You may like to take a look at the related application note for further details. We also need to check the memory that's used for what's called in this course register variables. For example, in designs that use reset-based mode changes, we rely on register variables to store the required mode between changes. We need to perform a check of the memory area in which these variables will be stored during power-on self-tests, and usually every time data are stored in these registers. Assuming that 32-bit registers are used, the test will usually involve writing the following values to each register and reading back each value again after it has been written to confirm the memory operation. We also, of course, need to check our peripheral. Once we're sure that our processor is operational, we need to check that it is fully connected to the outside world. This is likely to involve sanity checks on sensor inputs and moving actuators. We discuss such tests in video 5. We also need to perform environment tests on many systems. For example, we typically need to keep tabs on the CPU temperature to make sure that that's within the operating range for which the device has been designed to operate. For example, in an automotive design, your device might be designed to operate at up to 125 degrees Celsius. As the temperature approaches this level, you need to take care. You cannot guarantee the operation of the device outside the specified temperature range. Similar concerns arise with power supply voltages. Again, it can be useful if you have multiple processors to be able to have processor A check the power supply and temperature for processor B and vice versa. Again, this is another reason why multiprocessor designs can be particularly attractive in safety-related systems. That brings us to the end of this video. Please read Chapter 14 in the ERES2 book before you continue with the course. Thank you for watching.